Assalamu alaikum and a very warm welcome to my channel. Today we are going to discuss about the propagation of error or error accumulation. So in today's lecture we are going to find out the answer of a question that how error propagate in different operations. These operations include addition, subtraction, multiplication and division. So understanding how errors propagate helps quantify the reliability and accuracy of results. So with the help of a very simple proof, we are going to find out the answer that how error propagates in different operations. So let's proceed. So first proof is error accumulation in addition. So we have error accumulation in addition. So we are going to let x1 and x2 be two approximate numbers, and let y is equals to x1 plus x2. Secondly, let e1, e2 and ey be errors in x1, x2 and y respectively. So y minus ey is basically the error in y, is equals to x1 minus e1. E1 is the error of x1, and we have x2 minus e2, and e2 the error of x2, and that should be subtracted from x2. So we are going to simplify it. That should be x1 minus e1 plus x2 minus e2. So y minus ey, that is equals to x1 plus x2, and we have minus e1 and minus e2. So we are going to take negative sign as a common from both of these error. So that should be e1 plus e2. And we know that x1 plus x2 is equals to y. So we are going to substitute back, that is y minus e1 plus e2. So this should be cancelled with this, and we are left with minus ey, that is equals to negative e1 plus e2. So this negative will cancel out this negative. You will get ey is equals to e1 plus e2. So when we talk about the absolute error according to this, so absolute error is equals to mod of ey. That should be equals to mod of e1 plus e2 and mod close. So ey must be less than equals to mod of e1 plus e2. So this result can be extended to n numbers of terms, that is, if y is equals to x1 plus x2 plus x3 and up to so on to xn, then ey is equals to e1 plus e2 plus up to so on to en. So according to this, we may write it like this, that ey is less than equals to mod of e1 plus mod of e2 plus mod of e3, and this goes up to nth term. So we concluded that, therefore, it shows that the sum of absolute errors of n approximate errors doesn't exceed the sum of the absolute errors of the numbers. So that is the result of the error accumulation in addition. Now we are going to proceed towards the second operation. So we are going to see the proof of error accumulation in subtraction. So secondly, we have error accumulation in subtraction. Okay, for that we are considering the same thing, that let x1 and x2 be two approximate numbers, and let y is equals to x1 minus x2. Because of this subtraction, we are going to subtract both of these approximate numbers. Secondly, we have let e1 and e2 and ey be the errors in x1, x2, and y respectively. So for that, we are going to choose the same y minus ey and x1 minus e1. E1 is the error in x1. So we are going to subtract this error from x1. Then we have a negative sign. Previously, we used the positive, and here we are using a negative sign because we are finding out the error accumulation in subtraction. Secondly, we have x2 minus e2. So e2 is the error of the x2. So we are going to simplify it. X1 minus e1, from here minus x2, and this minus will become plus e2. So for that we have ye minus ey, that is equals to x1 minus x2, and on the other side we have minus e1 plus e2. So y minus ey, that is equals to x1 minus x2, and again we are going to take negative sign as a common, so that should be e1 minus e2. So in that case, we already know that x1 minus x2 is equals to y, so we are going to substitute it back, that is y minus e1 minus e2. So this y should be cancelled with this, and we are left with negative ey and negative e1 minus e2, and this negative will cancel out with this negative, and we will get ey e1 minus e2. So when we are going to find out the absolute error of this, so it means that absolute error is equals to mod of ey, that should be equals to e1 minus e2. So mod of ey is less than equals to e1 plus e2. So we used plus here because when we have a negative sign in mod, so when we apply the mod, the negative sign will be resolved to a positive sign. So this negative with e2, so because of the mod, the negative sign will be resolved. So we are left with plus. So this result can be extended to n numbers of terms, that is y is equals to x1 minus x2 minus x3 and up to so on to negative xn. Then ey is equals to e1 minus e2 minus e3 and up to so on to negative en. So when we apply the absolute error, so ey is less than equals to e1 plus e2 and up to so on to en. This is the same case become as previously we did in the addition. So the result will be same, that simply we can say that therefore it shows that the subtraction of absolute errors, basically when we are applying the subtraction, this subtraction will be converted into addition. So errors of an approximate error does not exceed the sum of the absolute error of the numbers. Okay, let's proceed to the error accumulation in multiplication. We have the third case. So here in this case, we are going to let x1 and x2 be two non-zero approximate numbers and y be their product. That is, y is equals to x1 and x2. Secondly, let e1, e2 and ey be errors in x1, x2 and y respectively. So in this case we have y minus ey, that is equals to x1 minus e1, and we use the product, that is multiplication, so x2 minus e2. So here we are going to multiplying each term and we are going to open our brackets. So first of all we have x1, x2, then we have e1, e2, then we have e1, x2, and then we have x1, e2. So we are going to ignore e1 and e2 because these are the small quantities, and when they are multiplying with each other they will become more smaller. So ignoring e1, e2 because e1 and e2 are small quantities. So y minus ey, that is equals to x1, x2. This goes to 0, or we just ignore it. So simply we write it e1, x2 minus x1 and e2. As we know that x1, x2 is equals to y, so we are going to substitute back into the previous equation. So it's become e1, x2, x1, e2. So this will cancel out with this, and we are going to write minus ey, that is equals to minus e1, x2 and minus x1, e2. Now from this part we are going to take negative sign as a common, so it's become positive inside, so this will cancel out with this and you will get e1 x2 plus x1 e2, right? So after that we are going to see according to the absolute error, so that should be ey, that is equals to e1 x2 plus x1 e2. So according to the relative error, we must have absolute error over y. So that is absolute error is ey over y. So for that part, we are going to substitute the value of ey, that is e1 x2 plus x1 e2 divided by y. And we have the, for here, we are substituting this value e1 x2 plus x1 e2, and here we are substituting the value of y, that is we just simply say like this, that y is equals to x1 x2. So e1 x2 plus x1 e2 divided by x1 x2 mod. So we are going to separate the denominator on both of these terms of the numerator. So it should be e1 x2 over x1 x2 plus x1 e2 over x1 x2. So this should be cancelled out with this and this with this. So it should be r dot e, that is equals to e2 over x1, and that should be, sorry, this is e1 not e2, so e2 over x2. So from this we may write it like this, that relative error is e1 by x1 plus e2 by x2. So after that we may write it like this, that relative error must be less than e1 over x1 plus e2 over x2. So which shows that the relative error of the product of any two non-zero approximate numbers does not exceed the sum of the relative errors of the approximate numbers. So we can extend it to nth term. So we may say that this can be extended to the product of n non-zero approximate number. That is y is equals to x1, x2, x3 up to so on to xn, where x1, x2, xn is not equals to 0. So if we write it that x of I is not equals to 0, then I must be equals to 1, 2, 3 up to so on to n. So relative error is equals to Ey over y less than equals to E1 over x1 plus E2 over x2, and this should be extended to En over xn. Next, we are going to see the error accumulation and division. That is the last proof. Error accumulation in division. So in this, we are going to consider the same numbers that let x1 and x2 be to non-zero approximate numbers and y be their division. So that is y is equals to x1 by x2, because we are going to see the proof of the division. Secondly, we have let E1, E2 and EY be errors in x1, x2 and y respectively. So in that case, we have y is minus EY, and so we have the division. So we write y1 minus E1 divided by x2 minus E2. So here we have y minus EY. That should be equals to x1 minus E1, and we shift the denominator into the numerator, and when we shifted this denominator into the numerator, so here we have the power 1. So when it goes to the numerator, the power becomes negative 1. So in the next part, we are going to simplify it. We are taking from the first x1 common, so it should be E1 by x1, and from the second we are going to take x2 raised to the power minus 1 common, so it should be 1 minus E2 by x2 and negative 1. So we simplify it to Ey, that should be equals to x1 and x2 raised to E1. So 1 minus E1 over x1 and 1 minus E2 by x2 negative 1. Now, for the second case, we have a negative power. So for the negative power, we are going to expand it by using a binomial expansion. So first, I'm going to explain you that what is the general formula of binomial expansion, and then we are going to expand it. So binomial expansion. So the general formula of binomial expansion is we have a plus a negative sign. This is applicable for both, and we have an, so plus and negative, and an minus 1, b, then we have a plus. This remains plus for both the cases if you have a positive and a negative in between of two numbers. Then you have n minus 1 by 2 factorial, and n minus 2 b2. Then you have plus minus, then you have n minus 1 n minus 2 over 3 factorial, and here you have n a n minus 3 and b raised to 3 plus up to so on to bn. So this is the general formula of binomial expansion. Now we are going to expand this according to this formula. So first of all, we are going to expand it and then we are going to back substitute it into this equation. So we have 1 minus e raised to the power 2 over x to negative 1. So we are going to use a negative signs formula of binomial expansion. So for that case, this one is our a, this whole is our b, and this negative n is our n. So when we are expanding it, it should be 1, negative 1, negative, then you have a negative 1, then you have a 1, and upside we have negative 1 and negative 1, and for b we have e2 over x2. In the next term we have plus negative 1, negative 1 and negative 1, bracket close, by 2 factorial. Then we have an n which is negative 1, and then we have a, that is 1. So negative 1 and negative 2 in the exponent part, and then you have e2 by x2 raised to 2. So in the third we have again negative, so we are moving down. So for the n case we have negative 1, negative 1 and negative 1, and then we have negative 1, negative 2 over 3 factorial. So here we have negative 1, so 1, negative 1, negative 3. So in that case we have e2 by x2 raised to 3. So e is very small in that case also, so we are neglecting the higher powers of e. So in that case we have e raised to 2, so this should be neglected and this should also be neglected. So we are just considering this part. So when we are considering this part, so it should be simplified to 1 minus e2 over x2 raised to minus 1. That should be equals to this one, because when we have a negative power of 1, any power of 1, it gives you 1. Either it's negative or positive. So here when we simplify it, so we will get plus e2 x2. So when you simplify it, you will get negative 2. So this is 1. So 1 times negative 1, you will get negative 1. And when this negative 1 multiply with this negative, you will get positive 1. So we are going to substitute this value here. So we may write it like this, that y minus e y, that is equals to x1 and x2 1 minus e1 over x1, and here we have a negative power, so we directly substitute this value here. So that is 1 plus e2 by x2. Now we are going to simplify it. Y minus ey, that is equals to x1, x2 raised to the power 1, and we are multiplying these bracket, so it should be 1 plus e1 by x e2 by x2 and negative e1 over x1 and negative e1 e2 over x1 and x2. So again we are neglecting this term because both are the errors multiplying each other and these are very small. So when two small quantities multiplying each other, and this become a more smaller quantity, so that's why we are neglecting e1 e2 by x1 and x2. So the expression simplified to as y ey, that is equals to x1 x2 raised to 1 1 plus e2 by x2 minus e1 over x1. So then we are going to multiply this x1, x2 with the negative power inside of the bracket. So that should be x1, x2 negative 1 plus x1, x2 negative 1, and that should be e2 by x2 minus x1, x2 negative 1 and e1 by x1. Now we know that y is equals to x1 by x2. So if we shift x2 on the upper side, so that should be like this. So we are going to substitute this value back into the equation. So it's become y plus x1, x2, negative 1, e2 by x2, x1, x2 raised to minus 1, and e1 by x1. So we will cancel this one with this one. So we are left with ey is equals to x1, x2, negative 1, e2 by x2, negative x1, x2, negative 1, and e1 by x1. So we are going to shift this x2 with a negative power to the denominator side to make it a positive. So it's become e2 x1, and in the lower side we have x2 and x2 minus we have e1 x1 over x1 and x2. So this should compile and it becomes e2 x1 over x2 raised to 2 minus e1 x1 over x1 and x2. So this should be cancelled out with this one. So we will write e2 x1 over x2 raised to 2 minus e1 by x2. So we are going to take negative sign common. So that should be e2 x1. Here we have a positive sign. So it becomes negative when we take negative sign as a common, and this should become positive. We will cancel out with this one and we are going to adjust that. So second one is e1 by x2 and negative e2 x1 by x2 raised to 2. Okay, so after that we are going to write the relative error. So relative error is equals to absolute error over y. So that should be equals to e raised y over y. So we are going to substitute back. So we know that ey is equals to e1 over x2 minus e2 x1 by x2 whole square, and in the denominator we have y, that is equals to x1 divided by x2. So we are going to simplify it. So for this simplification case, I'm writing e1 x2 negative e2 x1 over x2 raised to 2, and this should be shifted to the other side. So the numerator and the denominator part should be reversed. When we shift the denominator in the numerator, so if the denominator part is in fraction, so their numerator and denominator should be reversed. So after that, we are going to multiply inside e1 over x2 multiply by x2 over x1 minus e2 x1 over x2 raised to 2 into x2 by x1. So we will cancel these terms and we will get e1 over x1 negative. This will be cancelled out with this one and this will be cancelled out with this one. So we will get e2 by x2, and that is basically the relative error. So after that, we know that relative error should be less than and equals to E1 by x1 plus E2 by x2. So that is the fourth case, that is the error accumulation in division. So let's discuss another case, that is the error accumulation in power and roots. That is the fifth one proof. That is error accumulation in powers and roots. That is also very important thing to know. So for the proof of this, we are considering let x be an approximate number and y be a number such that y is equals to x raised to n, where n is a real number. Secondly, let e and ey be an error, be an errors in x and y respectively. So yes, for that we are considering y minus ey same as we did before and x minus e. In that case, we are considering a one approximate number x. So the error of x is e. So we are going to subtract this e from x. So we are considering a power. So the power should be n. So here we are taking a common of x raised to n, and that should become this. So again, we are going to apply the binomial expansion. So for the binomial expansion, I am writing here direct. That should be 1 minus ne by x plus n minus 1, because already we have the power n. So we are just replacing it. So that should be a 2 factorial. So multiply by e squared by x squared plus up to so on, right? So again, we are neglecting the higher powers of e. So we are neglecting this term and we are considering 1 minus ne by x. So after that, this is y minus ey. So after that, we need to multiply this xn inside the bracket. So y minus ey, that is equals to xn and minus xn, and that should be like this. And exn over x. So we are going to simplify it, xn minus ne, and this is power is 1, so we shifted on the numerator. So that should be xn minus 1. So as we know that again that y is equals to xn, so we are replacing in the previous equation, that is y minus nex n minus 1. So we are cancelling out. We are left with ey minus ne x n minus 1. So we are just cancelling this negative and we will get ey nex n minus 1. So after that we have a relative error that should be equals to absolute error over y. So for that case, I am writing that for the absolute error we have ey over y. So for that case we have nex n minus 1 over xn, because the value of y is xn, we already know it, right? So after that we have xn and xn, and that should be cancelled out. So the remaining is x raised to the power minus 1. Because here we have xn dot x negative n. So in the denominator we have xn. That should be cancelled out with this one, and we are left with this. Okay. So after that, we are going to simplify it just like this, that n e, and we are shifting this negative power to a positive power. So we are just shifting it into the denominator, should become a positive. So n, so here we have e by x. So according to this proof, we see that which shows that relative error of nth power of n approximate numbers equal n times relative error of that number. So yes, students, these are the simple proofs that shows the error accumulation in addition, subtraction, multiplication, division, powers, and root. So thank you so much for watching, and don't forget to subscribe my channel. Take care of yourselves, and Allah Hafiz.